right, class, so now we're going to start chapter 2, which discusses sequences. So section 2.1 is all about describing sequences. So it's probably a good idea to define what a sequence is in the first place. So a sequence is simply a list of ordered numbers. For example, here is a sequence 0, 1, 2, 3, 4, 5. So these are just the natural numbers, right? In a sequence, we care very much about the order numbers are in. So we use variables to represent the terms in a sequence. So we'll have a sub 0, a sub 1, a sub 2. The numbers in the subscripts are called indices. That's just the plural of index. And to refer to the entire sequence, we'll write parentheses a sub n for all n element of the natural numbers. Remember, the natural numbers are from 0 to infinity, and they're just positive numbers. So let's look at these. Can we find the next terms in these sequences? So here I have the sequence 7, 7, 7, 7, 7, 7, 7. Can we guess what the next one is? Yeah, it's probably going to be a 7. How about this second sequence? I have 3, negative 3, 3, negative 3, 3. What do we think the next term is going to be? Well, the next term is going to be a negative 3. How about this example 3 right here? I have 1, 2, 4, 8, 16, 32. What am I doing each time? Well, it looks like I'm multiplying by 2. So the next answer would be 64. Now, given a sequence, we can guess, but there's no way to be certain what comes next without a definition or a formula. So a closed formula for a sequence is a formula using fixed operations on n. So this is what you'd normally think of as a formula in n. So let's find the first few terms of the following. So if I have a sub 0, that'd be 0 squared, which is 0. A sub 1, that'd be 1 squared, which is 1. A sub 2, that'd be 2 squared, which is 2. Next, I have a sub n equals m plus 1. So I'd have, for a sub 0, 0 plus 1 over 2. So that gives me a half. For a sub 1, I have 1 plus 1 over 2, which is 1. For a sub 3, I have 2. I have 2 plus 1 over 2, which is 3 halves. And it'll keep going like that. So we do that by plugging in the natural numbers. A recursive definition, this is also sometimes called an inductive definition. We have a whole section on induction at the end of the chapter. Consists of a recurrence relation. So an equation relating a term of the sequence to previous terms. And in order for that to happen, we have to have an initial condition, right? So we need to know what the first term of our sequence is. Or in some cases, the first couple terms. So let's find the first few terms of the following. So now I'm going to have a sub 1, which equals a sub 1 minus 1 over 2. Well, a sub 1 minus 1 is a sub 0, which we have defined for us. So I have 2 over 2, which is 1. Now I have a sub 1. So if we're going to find a sub 2, that's going to be a sub 1 over 2, which is 1 over 2, which is a half. If I want to find a sub 3, that's going to be 1 half divided by 2, which is 1/4. And it's going to keep going on like this. So you would get 1, 1 half, 1/4, 1/8, 1/16, 1/32, and so on and so forth. Now let's change colors. So for the second one, I have a sub n equals 2 times a sub n minus 1 minus a sub n minus 2. Okay, so in this case, my next term relies on the previous two terms before it. So if I have a sub 2, that's going to be 2 times a sub 2 minus 1 minus a sub 2 minus 2. That gives me a sub 2 is 2 a sub 1 minus a sub 0. So that gives me 2 times a sub 1, which is 4, minus 3, which is 8 minus 3, which is 5. A sub 3 is going to be 2 times a sub 2 minus a sub 1. So that gives me 2 times 5 minus 4. 2 times 5 is 10 minus 4 is 6. And let's find a sub 4 real quick. That's 2 times a sub 3 minus a sub 2. That's going to be 2 times 6 minus 5. 2 times 6 is 12 minus 5 is 7. Oh, this is going to be a really boring sequence if it ends up going up just by 1 every single time. Ha! I wanted to share with you guys some common sequences and their formula. So the first common sequence I want to talk about is square numbers. Square numbers are when I just take n and square it. Triangular numbers are when I can put the number of dots in a triangle, like 1, 1, 2, 3, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So that's something you can definitely check out in the book. Then I also have powers of 2, so like 2 to the 1, 2 to the 0, 2 to the first, 2 to the second, and so on and so forth. The last sequence I'm going to talk about is the Fibonacci sequence. This is one of those reoccurring definitions where I define my first two terms to be 1, and then what I'm doing is adding them together. So 1 plus 1 gives me 2. 1 and 2 give me 3. 2 and 3 give me 5. 4 is not in that sequence. Shame on me. So, given a sequence, we can define a new sequence, right, where that sequence is the sum of the elements in A. So let's let a sub n equal 2 to the n. So we have the sequence 2 times n. So the sequence 0, 2, 4, 6, 8. So b sub 0 equals a sub 0. B sub 1 would be a sub 0 and a sub 1, which gives us 2. B sub 2 would give us all the elements of A up to 2 added together, so 0, 2, 4, and that would give us 6. B sub 3 would equal a sub 0 plus a sub 1 plus a sub 2 plus a sub 3, which equals 0 plus 2 plus 4 is 6 plus 6 is 12, right? So that's how we write this in notation, where I is our index, all the way in is the number of terms in our sequence, and this symbol right here, this capital sigma, is telling us to find the summation. This is called summation notation. Okay, so let's use sum notation to rewrite the sums. I don't want you to calculate the sums, I just want you to rewrite the sums. So here I have the numbers 1 through 100. So here I have the sum from I equals 1 to 100, and I'm just adding up in a sub I, sorry. Right, so I have 1, 2, 3, where a sub I in this case is I. So let's just write and I is our index. Next, now I'm taking the square. So this is 2 to the I. Let's use I. So this equation right here is 2 to the I power, where I starts at 0, right? Because 2 to the 0 is 1. So now I have the sum from I equals 0 to 50 of 2 to the I.